Hello everybody, today we're talking about current and resistances, right? Well, first of all, let's understand how electrons travel to point A to point B. Well, let's imagine that we have a little light bulb here and we have a wire here, right? Now, perfectly. What we usually think about when we think in circuits is that electrons will work to travel really quickly through this cable, and this is how it will light the bulb, right? But that's not what actually happens. What actually happens is that a lot of electrons are pushing each other through the cable, and thanks to that we have the notion that they are passing through really quickly. Well, they are not passing really quickly. They are only pushing each other, which gives us like um, the sensation they are passing really fast, but they are not actually passing that fast. Great. Um, for example, now that we have that, let's see what charge density is. Well, charge density it's given by the formula J I over A. Right? Now, I is current and A is area. Looking at this formula, now we know something pretty quickly. We know that there's a direct relation between the current and the area to give the charge density, right? Now, if the area could be a millimeter square or centimeter square or whatever meter square, and current is given by the ampere, right? We sometimes use it as amp, whatever. Now that we know that, we will pass to the next concept, alright? Now, which is the next concept you would say? Well, very simple. Let's talk a moment about resistivity, alright? Resistivity is given by the rho letter in Greek, and it is basically the capacity of a material to not let the electrons pass through it, alright? You would say what is the inverse of the resistivity? Well, it would be basically 1 over rho, right? Yes, I know that's logic, but that also means this, which means conductivity, which inversely of the rho, conductivity is the capability of a material to let electrons pass through it, right? For example, a good conductor material would be copper, as we all know, aluminium, or the best one would be silver, but we all know that they do not use that because it's pretty expensive, right? Great. Now that we have this concept, we will pass to the next one, alright? Perfectly. Now, we all know these two rules, right? The Ohm's law. We all know this. It's equal to voltage equals, let's put it better here. Voltage equals current times the resistance, right? Perfectly. But there's another one that most of us, we don't usually know it. It is called the Paulette law. Right. Perfect. Now, what Paulette's law let you do? Well, it lets you calculate the resistance of something, right? And it's given by the resistance is equal to the length divided by the area times the resistivity. Do you remember the resistivity we were talking about a few seconds ago? Well, we have it here again. Great. Now, you would ask yourself, well, I'm not using this rule too much. Not, but it will maybe lead you to answer a few other problems, such as, for example, we have with this simple stuff that the resistance is, let's erase just a few seconds this, the resistance is equal to this, right? Now, let's replace it, right? We will know that voltage is equal to the current times rho length divided by the area, right? Now, do you remember a few seconds ago we defined J is equal, which this charge density is equal to the current divided by the area, right? Well, if you notice here, we have it again, right? So, voltage will be the same as charge density times the resistivity times the length, right? Great, perfectly. Now that we know that, I may ask you, can you get the electric field with this simple data? Well, I didn't know until a few days ago that you could get the electric field getting this, right? Electric field, let me erase it so we all can see it. Electric field times the distance equals charge density times rho times the length, right? Now, this distance means this d of the electric field means the distance the electric field has some range, right? It's the range that this electric field can get. And is this length, you may ask yourself, equal to that? Well, actually yes. So, as you see, we can eliminate this L of the length and finally eliminate the distance of range to the electric field. Great! So we have this small formula. Electric field is the charge density times the resistivity, right? Perfect. Now that we get that, we also can get that the charge density is equal to the electric field divided by rho, which is the resistivity. Now, do you remember a few minutes ago that rho is 1 over rho means, let me write it somewhere else, here. Rho, 1 over rho, imagine there's a 1 over rho, it's equal to the conductivity, right, which is the inverse of resistivity. Well, let's see. Now, once you do that, you can get that the charge density is equal to the electric field times the conductivity, right? Perfect. This is more or less what all the Ohm's law comes from, right? Now, let's see a really fast and small problem. So, do you remember with capacitance that we talk about that how to calculate the capacitance on a system, right? Well, let's do something really simple and really fast, which will be, let's have a small battery here, 9 volts battery, imagine, that doesn't matter right now, and we have resistance here, other resistance here, and let's see, 5 ohms. Ohm is the unit to calculate the resistance, and let's see again 6 or so ohms, right? You more or less can see it, more or less not, whatever. However, let's rewrite this, let's move right quickly. Right? Perfectly. Now, it's pretty simple to calculate the resistance of this circuit, right? It would be basically 5 log 6, right? That's how you get the total resistance of a system when it's in series, alright? So it would be 11 ohms, right? Perfectly. Now, let's imagine that you want to calculate the total resistance on a system, but it's not in series, it's in parallel, right? So let's imagine we have something like this. It is again 5, and we will be like 5 to make easy the numbers, right? Now, it's just like calculating the capacitance when it's in series. You are 1 over R total equals 1 over R1, R2, or blah 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 blah. So you will get 1 over 5 plus 1 over 5. Right? To make this thing a little bit simple, it means 2 over 5, right? If we change the size and we move R total to the upper side, R total would be 5 over 2. Would be 2.5 or something like that, amperes. Ohms. So we remember that perfectly. Now, in the case we have both, let's imagine we have a parallel and a series circuit. Yeah, on here, right? Perfectly. We have a parallel such as, let's put another resistance here, right? Let's see, it's 2 ohms, 2 ohms, sorry, 2 ohms, 3 ohms, and 6 ohms. Alright, perfectly. Now, what you do in these cases is to slowly eliminate from the inner part to the outer part the resistances, right? Now, how do you do that? Let me turn off this light to see if this looks better. Kind of. Well, how do you do that? Perfectly. Well, as we see, it is kind of more in the inside the 6 and the 3 ohms part, right? And let me turn it again, it didn't work very well. Perfectly. Now, as we have already said, this is a parallel circuit, so it would be 1 over 6 plus 1 over 3, alright? This, I will put this RP would be resistance partial, and that would mean 3 over 6 would be 1.5 ohms, right? Now, this part simply simplifies to 1.5 ohms, right? This will simplify to 1.5 ohms. You say, great, now we have a simple series circuit, right? Now it's 2 plus 2 plus 2 plus 1.5. The resistance total would be 4.5 ohms, right? Perfect. Now that we get that, we can get to another new topic, right? Now, there was a Russian guy called Kirchhoff that said, that was like, oh, these circuits are pretty simple. I want something harder, and he said, oh, I'm Russian, I will put a new battery in the circuit. So he invented a law to calculate all this, alright? He made the sorry, my marker decided not to paint anymore. Hold on a few seconds. Right. Kirchhoff law. Right? Now, what Kirchhoff basically did was that, hey, when I got more than one battery in a circuit or something like that, how will I calculate it? Well, he basically put two simple rules, which are not that simple maybe in the practice, but they are pretty simple in paper. He would say the sum of all the currents will be equal to 0, such as the sum of all voltages will be equal to 0, right? Now, you can work with this in a very simple way. Now, let's put a small sample, right? Now, let's put this way. We have a 12 battery here, I have something like this. I have a 15 volts battery here, a resistance here, another resistance here, another resistance here. Let's put it that these are our resistance. Let's put it that they are 5 ohms, 5 ohms, and 5 ohms. Alright? Well, now we have our circuit. Now, you would ask yourself, what the hell, right? Well, basically what you have to do is apply the laws Kirchhoff gave. Sorry. First of all, with the one that is all the sum of the currents, it's equal to 0, you will get something like, we will use nodes. In this case, it's very important that you understand that we use nodes, alright? In this case, this is node A and this is node B. Now, something that I didn't understand, so it may be useful for you when you are working with it, it's you are working with inner and outgoing currents. For example, you will have an I1, you have something like this, an I2 right here too. Sorry, my awful thing. This, as you see, this separates, so this one goes to I2, this one goes to I3, let's put it I3, and this one, again, because of the conservation of the matter, of the energy, it will be I1 again, right? Perfectly. Now, we know that A is the same as I1, so the ones that come in, you sum them, the ones that come out, you rest them. So it will be I1 less I2 less I3, and this would be, thanks to the Kirchhoff's law, equal to 0, right? Perfect. Now that we know that it's equal to 0, we can do the part of the node B, right? B. Great. So you have that I1, I2 and I3 are coming in, so I2 plus I3 minus I1 is equal to 0. Now, the interesting thing about Kirchhoff's law is that it gives you a lot of information, but it may be redundant. Not useless, but redundant. Yeah? Now, if you look at A and B, they are basically the same equation, but the only difference is that B it's multiplied times minus 1, or A it's time multiplied, A is B multiplied times minus 1, right? So you do not need one of these. So I eliminate B because I want. It's not necessary. B, you could eliminate A, but it's however you want to work. Now, the second part of Kirchhoff's law. This is again important. As I say, the first part of the intensity of the current, sorry, you will be working with nodes. Now, in this case, what you will be working with is with voltage and with fault loops. Hold on a few seconds again. You will be working with loops. But what I mean with loops, it's cycles or whatever you want. It would be the whole cycle, yeah? In Spanish they call it malla. I don't know if there is something similar in English. However, there's three loops. The one right here in the left part, the one on the right part, and the one of the global part. Alright? So, again, we said that the voltage, let me think where I'm going to write. Alright, let's write here. Voltage, the summatory of all voltages will be, equal to 0, right? It's important that we remember this, so we start assembling our stuff, right? Perfectly. Now, imagine, let's take this as B1, I put this one B1, B2 and B3, yeah, I call them like that. So, perfectly. We have B1, it's equal to this inner part, so it would be 12. So you get through it, you get to plus to minus, plus to minus. So you will have a lower voltage. So I put it that it would be minus 5 times the intensity, which this one is E3, minus 5. Sorry, I'm just writing in a very difficult position. 5 I1, right? We know that this voltage is equal to 0, right? Perfectly. Now let's go to the next voltage. Let me write a few seconds. I will be speaking, then I'll show you the equation because it's very complicated to write like that. Voltage would be, as we see in our loop, it's going that way. It starts at B. So as you see, it goes from minus to plus symbol. So what it will happen is that it would up our voltage, right? So it's the opposite of what happens in the other way around, right? Perfectly. Now it would be plus 5 times I3. This is pretty interesting. What happens here is that you pass a battery inverse. So what you would do is to raise the value of the battery. So it would be minus 15 volts, and it would be again from plus to less, plus to less, yeah. It would be again a lower voltage, right? So it would be minus 5 I2, right? And then you could build the whole circuit of right here. Well, it would be very simple. It would be B3. It's equal to a very simple. It would be you don't get through any. It would be less 15 volts. Let me move this a few seconds. Less 15 volts. From plus to less, it would be less minus 5 times I2. And this one, the last one, would be almost, we are almost done. And from minus 5 again times I1, and we finally put plus 12 volts. So you will be noticing something pretty interesting, which would be basically that B3 is what you get by getting summing B1 and B2. So again, as I said with Kirchhoff's law, they are kind of redundant from time to time. So this equation is not necessary after all. Anyway, from time to time you will need them. They are not always redundant. They sometimes are useful to solve problems, right? Perfectly. Now, as we get this, we say, hey, if we can get I3 by doing this stuff, right? I3, it's the same as minus I3 would be plus I2 minus I1, right? So you say, hey, I have I3 here and I1 here, right? So you could clear this up, and you will be getting that as I said, this part is not more important because you get that the voltage is equal to 0, right? To 0. So you would basically have that 0 is equal to 12 minus 5 times I3 minus 5 times I1. So hey, let's solve this part. It would be like, sorry, a few seconds. I1 would be equal to minus 5 I1 is equal to plus 5I3 minus 12, then you again change symbols, plus, less, erase this, and I1 is equal to, again this would be I1, it will be minus 5 times I3 minus 12 over 5, right? So, sorry, what you would do here is replace this value with this one, and again do that with the I2, which is right here. Once that you replace those values, you will get what I3 is. You will get the final answer of I. Once you get that, you will get a pretty interesting result, probably a negative current. And you will ask yourself, why would you get a negative current? Well, basically it would be because this is not planted the right way. The current is going backwards. So if you get a negative current, well, instead of going this way how it was originally going, what we'll be doing is going the other way around. So that would be everything with Kirchhoff's law.